All right, welcome to a special open house webinar dedicated to F equals MA competition preparations. This is an activity sponsored by the AwesomeMath Academy, and we will be talking about F equals MA and a few other things. And yes, we are recording right now. So let's see. Here's the agenda for today. First 10 minutes I'll spend talking about the competition and the rules. And then for about 45 minutes, we'll have something that looks very much like our regular level 1 physics class, except that this is open house now. We have many more people attending. Let's see, right now we have about 60 participants, which is great. Welcome everybody. 15 minutes of those 45 level 1 class minutes will be about Einstein's 1905 discoveries, his famous year of miracles, or miraculous year. And another 30 minutes we'll talk about medium hard but tricky F equals MA problems. After that, I might take a 5-minute break, and after that, I will talk about our AwesomeMath Academy online physics classes for anyone who is interested to join. And then we'll have another roughly 45 minutes of our level 2 class, again with guests. And 15 minutes of that will be about advanced problem-solving techniques, and another 30 minutes about some hard F equals MA problems. And even though the first half of this webinar is more like level 1 and the second half will be more like level 2, all of my level 1 and level 2 students have been invited. So I'm making sure that the material is interesting to all of them, so that level 2 students will not be bored. Don't leave me now that you know that the first half will be about level 1 primarily. There will be interesting stuff for everyone. Somebody is asking if there will be a recording of this. Yes, I will post it on YouTube. Okay, so moving on. About F equals MA competition, and you see a note at the bottom of the screen. You're welcome to ask questions through the chat box. Hopefully I'll see all of the questions. If by chance there are so many questions that I missed some, feel free to repeat it, okay? So F equals MA competition, it's classical mechanics only, so there is no relativistic mechanics, there's no electromagnetism, there's no thermodynamics or optics, it's classical mechanics only. Those students who qualify for the next level, which is US Physics Olympiad, they can expect to see electricity, magnetism, optics, thermodynamics, all of it. But at this level, F equals MA is classical mechanics only. It does not expect students to know calculus, so no calculus is needed. And let's compare competitions. Most of you are probably familiar with mathematical competitions. AMC as the first level, AME as the next, and then US Math Olympiad and International Math Olympiad. In physics, there is no first level competition. So F equals MA is already pretty hard, okay? It's at the level of AME. And then those who qualify go to US Physics Olympiad, and the final level is International Physics Olympiad. In 2018, it will be held in Portugal. Great place to visit. The competition problems are roughly 1/4 of them are easy. I would say very easy. About half of them are hard, and the last 1/4 are very hard problems. Of course, it's all relative, but the fact is that all problems, no matter how hard, carry 1 point, okay? And a common question is how many points to pass. This changes from year to year. But usually it's between half and 2/3 of 25 problems is needed to pass to the next level. Okay, let me see, I already see some questions. Where can we try for the US Physics Olympiad? That is a really good question. We do not offer a class at that level. And my philosophy is that those students who have qualified to go to US Physics Olympiad, they're actually ready to study themselves. And I've been helping some of my previous students do that, but you know, we don't have a formal class for that. Students who are ready for that are ready to study on their own. If my school does not attend F equals MA, is there any other way? I will talk about that in just a second, okay? So stay tuned. All right, so the last thing I had was how many points? Yeah, so usually it's between 1/2 and 2/3 of the problems, and it changes from year to year, depends. All right, and in the next page, I will talk about the rules, guessing, what kind of calculator, and so on. All right, so here is a typical first page of competitions. This is from 2017, and I would like to emphasize several, we're not going to read all of this, but several of the most important things here. So there are 25 questions, 75 minutes, and keep in mind, any of these rules can change in the future. So there's no guarantee that the rules will be the same when you try the test in January. But for the most part, they've been consistent from year to year. F equals MA expects you to forget the true value of G, 9.81, and to use a rounded value, 10, whatever SI units you like to express it in, either meters per second squared, that would be my favorite, but they call it newtons per kilogram, which is also good. Okay, you're expected to select the answer that is closest to the true result. You will see an example of that in the problems today. Sometimes they don't give you the actual result that you might be getting if you do the full calculation, but you're supposed to select whatever is the closest among the options they offered. Correct answers will be awarded 1 point. I already mentioned that. So that is regardless of difficulty. And keep in mind, there is no additional penalty for incorrect answers. So if you're running out of time and you don't have time to look at, let's say, last 5 problems, it is okay to be guessing. This rule has changed a few years ago. So that's an example of a rule that suddenly changed without much announcement. And so it is a good idea to read the rules before you start the test. It might change again. Okay, about calculators. Calculators are okay to be used, but they should not have anything in the memory. No formulas, no physical constants, no nothing like that. Okay, so a simple scientific calculator is probably the best thing to have. Okay. And again, all questions are equally weighted, and even though they're not necessarily the same level of difficulty. So I guess I've said it a few times already. All right, so that's about the rules. Let me see, there was one additional question. Which YouTube channel will this be on? That's a good question. I don't know. We don't have, I don't think we have an AwesomeMath channel. You can look it under my name, and you'll probably find it there. Okay. All right. So addressing some of the questions about F equals MA, where people can take it. Okay. Your school is the best place. However, not all schools register or participate in this competition. This is very sad. Just like with AMC, not all schools participate. So people always look for alternatives. You can ask the organizers, AAPT. You can also check with your local math circles or local universities, colleges. You can ask homeschoolers, they often know things like that. If you're in our area, we are near Dallas in Plano, Texas. So if you're in Plano or Frisco or Allen or Richardson, if you're in this area, maybe even Dallas, that's not too far away, 30-minute drive, you can join us. Just send me an email and we can talk. Registration deadline for schools or centers or homeschoolers or whoever is registering is December 4th, so you don't have much time. If you are going to register on your own, you have to hurry up, and you have to have a proctor. Parents cannot proctor for their students. It has to be somebody not related to the students. Usually a retired teacher you might know, or a librarian or something like that. This school year, the tests will be on January 23rd and January 31st, and you can only do one of them. You cannot do both. So only 2 days in January are testing days. How to prepare. This webinar is a great start. You will see some really nice problems. Also, lots of self-study. You need to study and prepare. This is a really hard test. You cannot expect to just show up and win. So lots of self-study. And later, I will talk about our online physics classes, which can be very helpful. We have really great materials, and we provide really strong guidance for self-study. And I will give more information about our classes later, okay? Let me see. So people are saying my math circle does, so somebody is organizing that. UT Dallas, okay, I am not familiar if they organize it. I'm happy that they do. Do we have to memorize all of the formulas, or will there be a formula sheet? Good question. So what I suggest to my students is to prepare a cheat sheet as they study, as they work on problems, as they prepare. A cheat sheet, I think, is a very useful study tool. But by no means should you try to use it in the competition. It would be totally irregular. A day or two before the competition, you may want to go through the cheat sheet, through the list of your formulas. And if there is 1 or 2 formulas that you didn't memorize by solving problems, then just memorize it just before the contest. Even though you'll forget it a day or 2 later, you will have it in your working memory at the test. So that's a good strategy, I think. So please, no cheat sheets in the competition. All right. So let me see if there are any questions. If not, I'll continue, but if you come up with a question, feel free to shoot a question in the chat box. Okay. Is there a book that is useful for preparation? I don't know of a book that is good for this. I developed the materials for this class based on some foreign books, choosing problems that are appropriate level, and that works really well for our students. But you know, I've been recommending a few textbooks to my students just as a reference if they need to refresh their knowledge about, you know, some basic formulas or derivations. But really, in terms of problem solving, there are no good books that I could recommend. Okay. All right. Let me talk about something interesting. In our classes, I like to not only work on problems, but also talk to students about physics and famous physicists and their discoveries, their work. And that actually sometimes comes in handy at the competition because they can answer some questions with greater insight into the history of that problem. So this time I decided to talk about Albert Einstein and his miraculous year, Annus Mirabilis in Latin, 1905. We all know that Albert Einstein was a really famous physicist, perhaps the greatest of all time, ranking right there with Isaac Newton, and I would also add Archimedes. Yeah, we all know that he's famous, but many people really don't know why. Why is he famous? People will say because E equals mc squared. Yes, but that's not the only thing. That's not even the thing he got the Nobel Prize for. So let's talk about that and about his incredible year, 1905. So Albert Einstein was born in 1879 and died in 1955. He was born in Germany in the city of Ulm, and he got his PhD in Switzerland in 1905. And he became, after finishing his doctorate, he became a patent clerk in 1905. And maybe that was the lucky turn of events, perhaps, I don't know. Maybe he was getting bored at that job with his genius brain and started thinking about big problems in physics. And we will see how he resolved them in the next page. He got the Nobel Prize in 1921 for just one of those 4 papers he published in 1905, even though each of the 4 papers was worthy of a Nobel Prize. After he published those papers in 1905, he became a professor in Prague, in Berlin, later in Princeton, and you know, became famous for some of his discoveries. So let's talk about those discoveries, those 4 big discoveries in 1905. He had a few others later on. So one was about explaining Brownian motion. The other was about explaining the photoelectric effect. Another was special relativity. And finally, the energy mass equivalence, the famous E equals mc squared. Later on, he did much more work, much of it also worthy of Nobel Prizes. His theoretical work basically predicted that lasers can be made really powerful sources of light. He developed general relativity, which is the current theory of gravity. He worked in statistical physics, where we have Bose-Einstein statistics, and people have done things like Bose-Einstein condensate after that, and he contributed to really lots of interesting discoveries in physics. So let's talk about these four discoveries he made in 1905. So to understand their importance and how incredible they were, and to happen, you know, 4 of them in the same year, how incredible that year was, let's talk a little bit about the state of physics before 1905 and about Einstein's discoveries, okay? So in 1905, believe it or not, in 1905, some big names in physics and chemistry still were not convinced of existence of atoms, okay? It's hard to believe, but it is true. And even though Boltzmann at that time has already developed his statistical physics explanation of thermodynamics, you know, assuming that atoms of gas are little spheres bouncing with each other in a container, and you know, he devised formulas for pressure, and he basically derived all of thermodynamics formulas from the assumption that gas are little spheres bouncing around. Still, that did not convince those big names like Mach and Oswald. However, in 1905, Einstein was able to explain Brownian motion. Brownian motion was discovered by a Scottish biologist who looked through a microscope and noticed little particles of flower pollen floating in a liquid and having really strange random motion, and people could not explain why they were moving like that. And Einstein was the first to thoroughly analyze the idea that it was the atoms or molecules in the liquid randomly hitting on that pollen particle and causing its random motion. And he mathematically analyzed that idea and got some result that matched the actual observations. And really, that was the work that finally convinced last of those big names who were not convinced of existence of atoms. Okay, so that was a big discovery, big work in its own right, probably worthy of a Nobel Prize. Another thing, okay, the photoelectric effect, a little bit of history there, prior history there. In 1900, Max Planck explained the emission spectrum of a black body using a strange trick, E equals h nu. The energy that can be emitted only in the multiples of that of this smallest quantum of energy, smallest amount of energy that can be radiated. H is the Planck's constant, nu is the frequency of the oscillator or frequency of the radiation. Okay, Planck himself was a classically trained physicist, and he didn't like this assumption that he used in his paper that was the first to derive the black body spectrum, but it worked, and Planck himself thought it was just a temporary trick, that didn't really agree with classical mechanics, but he thought maybe sooner or later somebody will figure out why this was a useful, strange trick to use, and things will go back to the way they were in classical mechanics. However, in 1905, Einstein used that same formula, that same strange trick that Planck used to explain absorption phenomenon called the photoelectric effect. And that explanation, that paper in 1905, is the true beginning of quantum mechanics or quantum physics. Einstein realized that E equals h nu is a fundamentally true formula, true concept, that energy can be transferred not in any arbitrary amount, but only in multiples of this minimum quantum, E equals h nu. That is the work he got the Nobel Prize for in 1921. And really was the true beginning of quantum mechanics. Okay, now I'm throwing a lot of concepts around here, like Brownian motion or black body spectrum or photoelectric effect. I'm not going to explain anything else about them. I hope that you're intrigued enough and that you will go to Wikipedia or to your library or find some other resource and learn much more about these things. These are really fascinating things that you should learn about on your own. Find a book, find a good website, read about that. Okay, so the third paper about relativistic mechanics, special relativity, the history there before Einstein's discovery was that there were contradictions between classical Newtonian mechanics and Maxwell's equations of electromagnetism. People knew that there were some contradictions and didn't know where they were coming from. And there were several people who were trying to explain them, including Poincaré, the famous French mathematician, and the Dutch physicist Lorentz, and a few others. But it was Einstein who truly understood what was the problem, where was the problem. He realized that Newton's mechanics, even though it applies so well to our everyday life, even to explaining the motion of celestial bodies, planets and all that, Newton's mechanics had its limitations. And when people tried to reconcile Newton's mechanics with Maxwell's electromagnetism, they hit a roadblock. There was something wrong in Newtonian mechanics, and that was that the mass really is not a constant thing. It really depends on the velocity of motion of the object, and the true mass, we call it relativistic mass, is m0, the rest mass, divided by this factor. And if you try to plug in values for v that are close to c, the speed of light, you will see that m is getting bigger and bigger. And if you're getting close to the speed of light, it actually tends to infinity. And some people would say that's really the reason why you cannot attain the speed of light. There are actually better explanations, but okay, at this level, I think that explanation is fine. Anyway, Einstein basically introduced this correction factor called Lorentz factor. Lorentz actually used it first, but didn't explain everything with it. Einstein used it and was able to reconcile mechanics and electromagnetics. Okay, so let's see, there was one more, right? What was the fourth paper? Anybody remembers? What was the fourth paper Einstein published in 1905? Yes, E equals mc squared. Yeah, let's see. What's the history that preceded that? None. That was a totally new discovery. Nobody really called for it. There was no problem people are trying to solve and couldn't, and Einstein did it. This was a consequence of special relativity, totally unexpected, that E equals mc squared, that energy and mass are totally equivalent concepts, and that conservation of energy and conservation of mass have actually to be merged. As a consequence of this discovery, we can talk about nuclear energy, about atomic weapons, about many other things, and I'll just leave it at that. E equals mc squared initiated a lot of new events in the 20th century. Okay, so let me see some questions before I move on. So somebody is asking, what level is the Classical Mechanics by David Morin? Okay, I have two books by David Morin. They're both really good books. I really like them. They are probably, the collection of problems is probably the level of level 2 in our classes. So it does cover harder problems in F equals MA. And if there is a book I would recommend for preparation for F equals MA, that would be the one. And then Morin also has a book, basically theory, with lots of good problems, but the problems are typically harder than our level 2. So a little bit harder than what's needed for F equals MA. I would roughly say it like that. Okay, moving on. Let's see. So yeah, that was about Einstein and his big 4 discoveries. Perhaps his biggest discovery came about 10 years later, the general relativity, a totally new concept of gravity, space, and time, curvature of space, and predictions of light bending near big masses, soon afterwards confirmed during a sun eclipse in 1919 by Arthur Eddington. And yeah, I could talk about Einstein and his discoveries for much more, but let's not do that. Let's move on without problem solving, okay? So let's see. I'll be focusing today on 2015 F equals MA exam. And let's look at problem number 4, okay? I'll give you a minute to read the problem, and I'll then talk about it. So go ahead, read the problem. Okay, so usually it's a good idea to draw a little diagram of what's happening in the picture, in the problem. So a little picture about the problem. Let me see, I'll try to draw. So we have a horizontal surface, and we have a box with mass m, it's given 2 kilograms, and we are given that there is static coefficient of friction, there is kinetic, so if the box is moving, friction will be kinetic, and it is 0.9 of mu s. Okay, where is my mu? Something happened here. Okay, mu s. And there is a horizontal force of magnitude p acting on the object, okay? And the question is, let's see, the question is to analyze acceleration of that object versus the magnitude of that external force P. So as P increases, what's happening with acceleration? Okay, so definitely we expect, because there is static friction, for very small values of P, we expect no acceleration, zero acceleration. And then at some point when we reach the critical force P and overcome the maximum static friction, the object will start to accelerate. So because of what I said, that initially we expect zero acceleration, these two diagrams are not possible, okay? We expect to see something like we see in ABC, this initial part here. You know, initially until force P overcomes the initial, the maximum static friction, we expect that. Now, which one of these will we have, A, B, or C? Let's see. If we had C, that would mean that right after we overcome the maximum static friction, we simply continue like nothing happened before, like there's no jump between mu k and mu s. Really, that jump between mu k and mu s really is visible right here in these jumps here, okay? So it's not going to be this guy here. No, it's going to be A or B. Now let's see which one, A or B. These pictures are, these diagrams are not terribly quantitative, more qualitative, but still there is a distinction between them. What you can see is that roughly this diagram in B is a line that if we extend it, it would have a zero intercept, zero y-intercept, whereas the diagram in A does not have a zero, it has a non-zero y-intercept. So let's see, how is that important? So let's assume that mu k is equal to some number u times mu s, where u can be any number in interval, in closed interval 0, 1, okay? Then when P, our external force, is greater than the critical, the maximum static friction, mu s mg, we can write Newton's second law as follows. Ma equals the total force, right? And the total force will be external force P diminished by the kinetic friction, mu k mg. If I substitute, instead of mu k, I write u mu s, I can express A as follows. P over m minus this term u mu s g. P is our variable, so this is really a linear function of P. It has slope 1 over m, and the acceleration is that linear function with slope 1 over m, and intercept negative u mu s g, okay? If u is 0, so let me, maybe I can erase this so we have more room here. Am I able to erase this? Yes, it disappeared. So let's see. We were wondering what happens between A and B, which is the true one, okay? So if mu k is 0.9, let's look at B first. If mu k is 0, so that factor u is 0, then we would simply have A equals to P over m. That is a zero intercept, okay? That would be B. And this is not our case. Our case is with u equals 0.9. And that really looks very much like what we see in A. So I think I convinced you that A is the right answer, okay? So, okay, I think that's all clear. So let's move on. Maybe I can erase my drawings here. Let's see, how do we do that? Annotate, clear all drawings. Okay, very good. All right, so moving on to the next problem. The next problem is number 5 from 2015 F equals ma. I'll let you read the problem. I'll give you a minute to read and digest the problem and think about it a little bit, and then I'll talk about it. Okay, I think you had enough time to read it. What really happens if you launch a lead cannonball like this, it is not going to travel in a straight line because of gravity. It's going to travel something like this. Oh, where's my pen? Just a second. Okay, it is going to travel something like this. Okay, and it's going to hit the wall here. Let's denote this height here by, I don't know, H, or you could use Y or X or whatever letter you like. I'll use H right now. So the question is, by how much are we going to miss the target? So let's see. They gave us the exit velocity of the ball, 100 meters per second. The angle is 60 degrees. And this, the hypotenuse in this right triangle is 150 meters. In principle, if we could figure out the time of travel, you know, how long does this cannonball travel before hitting the wall, we could use that same time to say that height will be gt squared over 2. Okay, so if we figure out t, we are good. Let's see how we can figure out t. Well, there are multiple ways we can do it. For example, we could look at the horizontal component of motion. So in this direction, because it is constant, we can apply the formula t equals, what happened to my t? T equals to that distance x over the velocity in the x direction. And that really turns out to be x is these 150 meters, d cosine 60, that would be x. Okay, this is my x, this is my d. And divided by the horizontal component of velocity, which is v cosine 60. And we actually see that cosine 60 and cosine 60 can be canceled. We get d over v. And we can actually figure out from that that there is a better interpretation of what we are doing. We could simply say this distance of 150 meters divided by the exit velocity. We are pretending there's no gravity, and that is okay in this case. And we get that travel time, the time of flight in this case is 1.5 seconds, okay? Not difficult. However, there are some hidden tricks here, okay? Somebody might say, well, why can't we use the formula for time of flight that we learned, 2v0 sine 60 over g? Why would that be incorrect to do here? Well, the reason is simple, because that formula for time of flight on the bottom is really if the cannonball was flying all the way here, reaching the same height from which it was launched, okay? The formula 2vy, in this case v0 sine 60, divided by g is valid if we have a full trajectory of the cannonball, but that's not the case here. You can't even say that it's half of that, because it might be going something like this, and it would attain the peak only much later. Okay, we don't know. We are not given any of that information. Okay, so you cannot use that formula on the bottom. Okay, now we have time of flight between the launch and hitting the wall. So vertical displacement is, as we said, gt squared over 2. You plug in the numbers and you get 11.25 meters. Okay, now a few notes here. Okay, the mass of the ball here, 470 grams, was a totally unnecessary information. And you might think, you know, maybe my solution is not complete because I'm not using it. And yes, that's a common concern. But as you can see here, they will often give you extra information, trying to confuse you, okay? Another thing is what we mentioned when we read the rules of F equals MA, that our solution was 11.25 meters, and they did not offer that amongst the options A, B, C, D, E. But we found the one that is closest to that, okay, 11 meters, and that's what we use as the answer. Sometimes the discrepancy between the truly correct answer and the closest among options that they offer can be much bigger, maybe even an order of magnitude, but that's the rule. Circle or use the one that is closest to the true answer. Okay, so let me see some questions here. Let's see, where were we? Okay, somebody's asking, is the target 150 meters away or the cliff is 150 meters away? That's an actually really good question. If they did not provide the drawing, I would have thought that the cliff is 150 meters away from us. But the way they drew the picture, you know, this is not my picture, that's the picture provided by the competition. 150 meters is from the cannon to the target, okay? So somebody's saying 30, 60, 90 right triangle, and quickly got the result. Okay, but there is something wrong there. Yeah, look at that. T is not 75 meters. Something else is 75 meters. Okay, so let's see what else. Somebody's asking, where did you get h equals to gt squared over 2? Okay, that's a fair question. Okay, so when we have accelerated motion, we cannot use the formula like we had for constant velocity, that h is equal to vt. Okay, that's what I call middle school physics. When we have accelerated motion, as Galileo discovered, there is a factor of time squared, and also there is a factor of 1/2. And I don't have time to explain it again here, but I encourage you to look it up and find out about Galileo's discoveries, and this is one of them, that when you have accelerated motion, the displacement will depend on the square of the time, and this formula really works. Okay, so somebody is saying this is a great trick. I've seen it used before. Are significant figures important for F equals MA? Well, you can calculate your significant figures, your results, to, let's say, 3 or 4 significant digits. That's my recommendation. And then look at what they have. They will typically not have more than 2 or 3. So, you know, do your calculations with 3 or 4 and then see what they offer in their options. Okay. Somebody's asking, would you provide the presentation slides? I'll think about that, but definitely the video will be available. What other way can you find the time of flight? Well, one way, as I said, is to consider horizontal component, or you can go directly to considering traveling on this diagonal or hypotenuse line, pretending there's no gravity. So there are at least 2 ways to do it. How far is the answer usually from the answer choice? Usually they give you the correct answer among the options, but sometimes they don't. Yeah, I don't know. Let's see, what else? Doesn't the vertical displacement come from one of the... Yeah, it's from kinematics, yes. Are we allowed a calculator? Yes, as I mentioned when I read the rules, calculators are allowed, but you cannot have anything in the memory. And I would recommend a relatively simple scientific calculator, not graphing calculators, because you need to do quick calculations. You will not need to plot any graphs. Okay? How to obtain the video? Okay, I will probably post it on my YouTube channel. So in your email, find the spelling of my name and search for it in YouTube. Okay. Somebody saying, could you use one-dimensional motion equations? Well, here we actually did. We separated the problem into horizontal motion. That was this part of the solution. And then we considered separately one-dimensional vertical motion. That was this part. So yes, in fact, we did. Okay. When will the recordings be available? Maybe tomorrow. We'll see. Depends on how much editing I have to do. Okay, let's move on. Okay, maybe I need to erase all of these scribbles. Clear all drawing. Okay, very good. So let's move on to the next problem. We need to keep up the pace. I'll let you read it and think about it, and then I'll talk about it. There are actually two related problems, and we will cover both 7 and 8. The next slide is number 8. So go ahead, read, and think about it. Okay, so hopefully you had time to read it. There's a lot of information in there, but it turns out most of the information is totally unneeded, unnecessary. In this problem, we are told that the collisions are completely inelastic. And so what that means is that cart A will hit cart B and they'll merge together. Like imagine two ice cream balls hitting each other in the vast empty space of the universe. No gravity around, no nothing. Just two ice cream balls hitting each other and getting stuck together. You might think about Play-Doh too, but Play-Doh is not necessarily gonna merge that easily. I know I tried. But ice cream balls are a good analogy. So ice cream ball A hits ice cream ball B, and then they move together to the right and they hit ice cream ball C, okay, or cart C. And they again merge. And the question is, what is the final speed of cart C? Well, cart C will be a part of that new merged cart ABC. So, you know, they're maybe trying to trick us with that question here, but they'll be totally merged. So let's see. Maybe going one step back. When they say completely inelastic, what does that mean? First of all, that objects in the collision, they merge. And another thing is that kinetic energy is not conserved in all this. Some of the kinetic energy will be wasted on deformation of objects, so will turn into heat. But there is something that people sometimes will say magically remains conserved, and that's the linear momentum. Linear momentum gets conserved even in cases like this when there is merger, simply because there is no external force. When there is no external force on a system of particles or objects, in that case, linear momentum is conserved. All right. So because of that, this problem is actually very easy. Okay. There's no need to calculate much at all. No need to know 0 meter, 1 meter, 2 meter. No need to, worry about that. And we don't even have to consider what's happening when A and B collide first, and then separately when the cart AB collides with cart C. We can just look at the linear momentum before any collisions, and that would be P1 is mv, In fact, I should have written V0 because they gave it as V0. So before the collisions, it's just mv. The mass of cart A is m, its velocity is v0, so it's p1 is mv0. And then after all three carts are merged, the mass of them together is 1 plus 3 plus 9 m, so 13 m. And the new velocity, I call it w here, okay? That's the linear momentum after all collisions have happened. But as we said, linear momentum is conserved, so P1 is equal to P2, and we can equate these two things. So mv equals to 13 mw, and therefore w is v divided by 13. And now remember, I was a little bit sloppy, I didn't write v0, so the answer is really v0 divided by 13, as you can see here. So this was a fairly easy problem. You may have gotten scared from it because of all the information that's given in it, but you know, with a little bit of experience, you can learn how to ignore unnecessary information. These distances 0, 1, and 2 are not needed even in part A, so it's totally extra information that they gave us to confuse us. Okay, so that was easy, right? Yeah, bingo, problem solved. Very good. Okay, moving on. Problem 8 is a little bit harder. So it's the same setup, but number 8 is saying, assuming that all collisions are completely elastic, what is the final speed of cart C? Okay, that is a little bit more involved. This is not difficult, but is a little bit more involved in terms of computations. So let's see what is needed for that, okay? So here it is really useful to know the formulas that we showed in our class, and we even derived them in one of the homeworks. Formulas for elastic collisions, okay? So the conservation of linear momentum goes like this. The linear momentum before collisions is equal to the linear momentum after collisions. And because this is completely elastic, that tells us that kinetic energy is also conserved. You can think of billiard balls, and the kinetic energy is not wasted on deformation of objects. So kinetic energy before, with velocities v1 and v2, is equal to kinetic energy afterwards, w1 and w2, okay? So let's see, how do we solve this? We're not gonna do that right now, but in our class, or you can find it in good books, in Wikipedia, I'm sure, you get that velocities after the collisions are given by these formulas, okay? And what's interesting, in these competitions, you often get to use one of the formulas that are, you know, an auxiliary thing that you get from these equations, and that's V1 plus W1 equals V2 plus W. I just wanted to mention that here. We are not going to use that last formula here, but I just wanted to mention it, okay? So let's see, how do we use this, okay? Let's first consider the collision between A and B, okay? And because B is not moving, these formulas are really being simplified. So this is object 1, this is object 2, and so V2 is 0. So this whole term up here disappears, and we get the W2, the velocity of B after the collision. You can plug the formulas in, and you will get that VB is equal to that V0, the initial velocity of A, divided by 2. Let me show you how that works. Let's see. Where's my pen? Okay, so the velocity of cart B, I'll call it W2 right now. W2 equals to, this term here disappears, okay, because, I'm sorry, not that term. Let me think for a second. Oh, I'm looking at the wrong formula. Just a second, please. Okay, so if you look at the bottom formula, that first term, M2 minus M1 V2, disappears. I cannot reach it on my tablet, cannot write over it. but that first term disappears, so we get only 2 times, let's see, 2 times m1 v1 over the sum of the masses, m1 plus m2. Okay, so the mass is just m. v1 was v0, that's what was given, and then the sum of the 2 masses in 1 plus 3, so 4m. Okay, you can cancel 2m and 4m, you're left with just 2 downstairs, and that's v0 over 2. Okay, so that's how I got this part here. Okay, let me erase all of that. I'll need more space there. So clear all drawing. All right. So VB after the first collision moves with V0 over 2, correct? After B and C collide, B comes in with V0 over 2, and I use the same formula, the same bottom formula. This time V1 is my V0 over 2, the velocity of B, and V2 is 0 because C is static. And similar to what I did just a second ago, I get Vc, the velocity of C after the second collision, will be V0 over 4. And therefore, B is the right answer. All right. So I think that's what I had for the time being. I'll take a 5-minute break. Just to get a sip of water and give you a chance to rest, and we will continue. Let me show you what we are going to do next. During the break, you can read a little anecdote, my favorite, and after that, we'll talk about our AwesomeMath Academy online physics for about 10 minutes, probably less, and then we'll have some harder problems. We'll start with some advanced problem-solving techniques. And then we'll talk about some hard F equals ma problems. Okay, so stay tuned. I'll be back in about 5 minutes. You might see me shuffling some slides here for a second, but I'll give you that anecdote to read, okay, in just a second. So let's see, what are the problems we did not cover? I'll move them to the later. All right, so here is that 5-minute break slide with the anecdote that you can read and enjoy while I get a sip of water. We'll continue in less than 5 minutes, so don't go anywhere, okay? Okay, I'm ready to continue. I hope you liked the anecdote about how different expertise also carries with a different type of inductive thinking. I myself can wear some of these hats. I'm an engineer by training. I'm a computer scientist by training. I'll tell you a little bit about myself later. When I teach physics, I'm a physicist. When I teach mathematics, I'm a mathematician. But I was never a logician, okay? So that strictest way of thinking is not something I apply very often, but I do relate to all of these ways of inductive thinking. Okay. Yeah, somebody's saying conclusion, everybody's wrong. Yes, everybody except the logician. Logicians are the only ones with that, you know, full logical thinking. At least that's what this anecdote teaches us, okay? All right, I'm ready to continue. Okay, I see some people say hilarious. Yeah, it's a good anecdote. All right, so we covered things about F equals ma. We covered Einstein's Annus Mirabilis, and we talked about some medium hard but tricky F equals ma problems. Now I will tell you a little bit about the AwesomeMath Academy. Let's see, I'm curious how many people are. Oh, we have 70 participants. Very good. Welcome to everybody. We'll talk about the AwesomeMath Academy online physics classes briefly. And then for about 45 minutes, we will do some advanced problem-solving techniques, and we will work on some hard F equals ma problems, okay? I hope everybody's ready, so let's get started with this. Online physics, okay? I've been teaching it for, this is really the second semester only. This is a very young class. Before that, I taught it in a classroom. It was not online, but a classroom class for about a year and a half, I think. And as my students will confirm, we keep improving. It is already a very good class with excellent materials, but you know, we keep improving. I'm taking the feedback from students and parents seriously, and it is getting better and better every time we meet, I can say. We have a really good teaching assistant who is looking at homeworks and providing feedback, looking at each problem and doing some detective work to figure out where a solution may have gone astray. So it's all really tightly targeted at F equals ma. So the material we cover is strictly classical mechanics, although as you could see, we discuss all other parts of physics. It is no calculus in terms of math, but we do sometimes see calculus because some formulas that we use are derived using calculus. It doesn't mean that you need to know it for the competition, but I think it's a good idea to see how these formulas are derived and where those interesting factors like 1/2 or 1/3 in moments of inertia and even in gt²/2, you can derive that using integration. Where do these factors come from? Other benefits of this class are, you know, you can, working on these problems, AP classes, especially the mechanics part, will look fairly easy. And, you know, having learned how to solve physics problems in mechanics is also a great help. You can study electromagnetism and other parts of physics with greater ease because you know the main philosophy of physics, how to approach problems. And then also you can CBE, credit by exam, high school physics, and that's what I recommend to everybody who finishes level 1 physics, or of course level 2. My daughter, for example, when she finished level 1, she took a credit by exam physics and didn't have to attend high school physics. She could go directly to AP. To prepare for CBE, you will have to study a little bit more, electricity and magnetism, and maybe some optics, but it's all fairly easy. And, you know, with level 1, you can easily do that, okay? So in terms of level 1, it is a semester course. We have 11 units during 11 weeks. We don't meet every week. You know, we follow the schedule of the AwesomeMath Academy. We don't work for Thanksgiving and similar holidays. So it is 11 weeks in a semester. We do not expect any prior physics classes for that class, so this could be the first encounter with physics, but we do expect good, solid math at Algebra 2 level. So some trigonometry is really useful. And of course, in general, problem-solving skills that most of the AwesomeMath kids have. Students, after level 1, students will be ready to solve more than 1/4 of F equals MA problems. As I said, it is not enough to qualify to the next level, but it is a great accomplishment for somebody who tries F equals MA for the first time. And yes, I have been surprised by some of my level 1 students who actually qualified to the US Physics Olympiad after taking only level 1, but that is a rare thing, okay? In terms of level 2, it is also a 1-semester course, also 11 weeks. And we do expect some prior physics, at least high school physics, preferably some of the early AP physics classes. And in terms of mathematics, we expect pre-calculus level of knowledge. So trigonometry should be really good, and you know, drawing graphs and things like that. Students who finish level 2, if they're regular with their homeworks, will be able to do more than 1/2 of F equals MA problems. And then especially if there is a level of enthusiasm where students solve problems on their own, they will excel the F equals MA competition and have a really decent chance, really good chance to qualify to the next level. So what I'm saying is that level 2 is really a good preparation course for F equals MA, and also self-study is a really important component of that. Students should invest some of their own enthusiasm and energy in doing additional problems beyond the homework. And I'm here to help. Students often send me emails with questions, you know, I found this problem, here is the solution they offer, I don't get it, how do they do it, and so on. Okay. Spring registration is now open for our classes, so if you're interested, please consider registering for the spring. So let me see, there are a few questions. Let's see. Somebody's asking, are there problems that can be solved faster with calculus, although you don't need calculus? No. Typically, solutions really don't require calculus at all. There will be occasionally a single problem that you have to use calculus for, but it's just one really hard problem that if you don't do it, you can still qualify to the next level. I don't even know why they put such problems, but yes, sometimes there will be one problem in the competition that really requires calculus, but that's really an exception, not a rule, okay? So somebody's saying, is each question worth 1 point? Yes, that's what we said. Each question, no matter how hard or easy, is 1 point. So your score would be 6 if you get 6 questions. Yes, that's what I'm saying. Let's see, if a student had gotten 5 on the AP, where do you think she'll place for the competition? It is hard to say. F equals MA problems are significantly harder. Of course, there are some easy problems, but you know, half of the problems are at a level more difficult than physics AP C. My daughter took C, and yes, problems are really nice and hard there, but F equals MA problems are even harder than that. So it is hard to answer your question. Do you have a list of texts that you recommend? No, we had that question previously. No, I don't. There are some good books, but none of them really prepares you for F equals MA. Usually books are either too easy or way too hard. There is no right level that we could recommend for F equals MA. David Morin's books are really good. I would use them as a reference and as a source of problems, but you cannot rely on them to really give you the F equals MA type of problems for preparation. Will the current semester and the spring semester overlap? Yes, yes. Level 2 class in which you're currently, we will give it in the spring again, and the overlap will be more than 90%. I'm only slightly improving as we go, but the material is the same. And the main reason is exactly the fact that it's so hard to find the problems that are the right level of difficulty. You can find a lot of problems that are too hard for high school students, even the best students, you know, who go to physics Olympiad. You can find books that are really, really hard. And then there are many books that are way too easy. And finding that right difficulty for F equals MA is really hard. And I don't have a lot of such problems. And that's why I have only one level 2 class that we repeat every semester. All right. And by the way, if you are now in level 2, my recommendation really would be, I would say that you're ready to work on your own, to find a good book. I can advise you on that. Find a good book, find a good selection of challenging problems, and just work on it on your own. And of course, you can consult me when things get hard. But, you know, after level 2, I think students are ready to work on their own. I believe I would be just slowing them down. Yes, for sure. Okay, so let's see. That's all in terms of, oh, more questions. Let's see. Will spring have a level 3? No, I'm sorry. What topics are covered in the spring sessions? So it is the same level 1 and level 2, and you can go to our website and see what kinds of things we do there. Okay, it's classical mechanics. It's all classical mechanics for F equals MA. You mentioned a useful book, but I did not catch the title. Okay, so I will send a text message or a chat to everybody, and you can go on Amazon and find, there are 2 books by David Morin. Okay, I'm writing that, David Morin. He's a Harvard professor and has really good books. The one that is less expensive is a collection of problems. I would recommend that one as the first choice because it's not expensive and it has really good problems. And then the other book on mechanics by David Morin is more of a textbook. It's also very good. It's more expensive, about $80. And it also has some really good problems in there. Yeah. All right. Again, these problems often include calculus. They often are harder than what we need for F equals MA. So, you know, I cannot say that it's a perfect book, but it's probably the best I've seen. All right. So let's see. I think we are ready to continue. Oh, okay. A few more words about our classes. Okay. So our classes are a guided self-study. We have 11 units, and self-motivation is essential. Okay. On Saturday evening, dedicated to unit number N, let's be mathematical about it. On Saturday evenings dedicated to unit number N, we collect homework from the previous unit, unit N-1. We also release solutions for that previous unit, N-1. A few days later, students receive detailed feedback from their TA or TAs. On Saturday dedicated to unit N, we talk about what else but unit N. And class notes were available since previous Saturday. So they have about a week to prepare for that class. And keep in mind, I do not teach unit N in the webinar. I only answer questions about unit N because students are expected to prepare on their own. So self-motivation and self-study is essential in these classes. Okay, so people email me questions. Sometimes I answer them in email. Sometimes I collect them and talk about them in front of everybody. Or they ask me questions through the chat box like you guys do now. Okay. What else? Let's see. We also talk about famous physicists, like you heard me about Einstein and their discoveries. That's typically in level 1. And then in level 2, typically we talk about advanced ideas and problem-solving techniques. And often I treat level 2 students with the stories I tell level 1 about famous physicists. Okay. We also look at recent F equals MA problems. The reason I emphasize recent F equals MA problems is that roughly in 2012, problems in F equals MA became much harder than before. So if you want to see what kinds of problems you can expect in the next competition, you really need to look at recent F equals MA problems. Okay. Okay, so still talking about a Saturday on which we cover Unit N. On that Saturday, we release homework problems for that unit, and they'll do next a week later. And we also release on that Saturday the next class notes, so people can prepare for the next Saturday. So, as you can see, a lot of this hinges on self-motivation and self-study. Okay, and typically, I have a lot of email correspondence with students. Also, my teaching assistants have emails from students, so there's a lot of correspondence and interaction like that. Let me see some questions. So, yeah, so I see my message, two books by David Morin. Somebody's asking about Irodov's book. Irodov's book is harder than what is needed for F equals MA. Many problems are much harder. It is a good preparation book for US Olympiad, I think. Okay. Let's see. Somebody's asking how many questions are there on F equals MA? 25. Sometimes they have hard problems, but you can use them, you can solve them using dimensional analysis. Yes, we're going to see some problems like that in a few minutes. So yes, Irodov is a great book, not expensive, but it is very hard, okay? How much homework is there? There's a lot of homework. You have to spend at least 1 hour preparing for the next class and at least 1 hour doing the homework. Often it is more than that. Can students in middle school take this and qualify for Olympiad, or is it only for high school? I think the age doesn't matter. Middle school is just fine. Okay. Does level 2 cover dimensional analysis? Actually, we do look at a few problems related to dimensional analysis. It's a very easy topic, so I could not even say that we cover it. Okay. But yes, we do talk about it. There were more questions too. I'm not sure what that means. What do you recommend for fluids or waves? Typically, there are no problems about fluids and waves, okay? If there is one, maybe, but it really don't have to be solved with any special things there. I think there are 38 to 40 question tests before 2008. That's possible, I don't know. Does level 2 cover electricity, magnetism, Carnot engines, thermodynamics? No. Our classes, level 1 and level 2, are strictly dedicated to F equals MA, and we cover classical mechanics at a really difficult level. Okay. Is the homework like the online AwesomeMath math courses, or will there be more problems? It is probably similar. Every homework has about 5 to 8 problems, and they're not easy. Okay, so let's continue. Okay, let's see, where were we? Okay, so I think that's about it in terms of our online physics classes. Let me quickly introduce myself a little bit. Okay, this is me on this picture. I have an academically crazy family. My daughter Milena just started college. She's a Dedman Scholar at UT Austin. This Dedman Scholarship, you can call it like some people do, the Rhodes Scholarship of Texas. My son Nicola went to ISEF when he was in 9th grade, and he wants to go again. He liked it so much. And my wife, Alexandra, or Alex, she teaches innovation, and we are really crazy about academics, okay? I have a PhD in computer science, and I worked in industry all my career. I'm an expert in computer vision, in artificial intelligence, and currently working on self-driving cars. I guess I don't know how to spell driving. Let me quickly fix that. All right, that's good. That's better. So yeah, I work on self-driving cars at NVIDIA. Previously, I worked in some other companies, Delphi, TI, Interface. And I'm a passionate teacher of gifted kids in Metroplex Math Circle at UT Dallas, at the AwesomeMath summer camps where I taught Algebra 1.5, Numbers 1, and Geometry 1, and also at the AwesomeMath Academy with a couple of math talks, and also I really created these physics courses. All right, that's enough about me. And let's talk about some serious stuff now. Advanced techniques, and let's talk about some common approximations. And I'll write a few formulas here because the next problem will use some of that stuff, okay? So let me find my pen, okay, and my tablet. Okay, so in physics, very often we get some equations that, that turn out to be too complicated to solve quickly, okay? Maybe you can program a computer, do some numerical analysis, and solve it like that. But very often you actually don't have to solve that complicated equation. You can do some approximations, and that works quite well. And most of these approximations can be summarized as follows. Let me write a few of them. So commonly we will assume, let me choose a yellow color here, okay? So let's say that we are dealing with x, which is really a small number, okay? Maybe I'll write it like this. X is approximately 0, or maybe I can write it as absolute value of x is way, way less than 1. That's another way we write it. Or we just say small x, okay? And all of the formulas that I write next, you can check on your calculator by plugging in values like x equals to 0.001, or even smaller, maybe even bigger, 0.1 might work as well. So you can check formulas that I will write next by plugging in that value. Okay, so let's see. A very common approximation that we use is sometimes in equations we get sine of x, and we know that x is very small. In that case, we can simply replace sine x with x. Okay, I'll write it like this. Sine x is approximately x. Just keep in mind that x must be in radians, cannot be in degrees. Okay. All right. Another common approximation is this. E to the power x can be approximated with 1 plus x. Okay. And another one, 1 plus x to the power a, that can be replaced by 1 plus ax. Okay. A special case of this last one, I'll give you a few special cases that are commonly encountered. If you have 1 over 1 plus x, that can be replaced by 1 minus x. If you have a root of 1 plus x, you can replace that by 1 plus 1/2 of x. And you can come up with others like this, but basically this is the main idea. Okay. Somebody is complaining about the sound lagging. I apologize for that. Maybe the internet is a little bit slow. I don't know. Hopefully you guys can hear me well. Okay, so these are some common approximations that we use in physics to simplify equations, and this can work really well. The smaller the value of x, the closer it is to 0, the better the approximation will work. Okay, so let's move on. Let's see a problem where this was useful. Annotate, clear all drawing. Okay, so let's look at this problem. This was a problem in 2016, F equals ma, problem number 7. I'll let you read the problem, and we're going to talk about it. Okay, hopefully you had time to read it. Let's see what the problem is about. Okay, this is the solution they give in F equals ma on their website. I'll let you read that, and you can see my comment here. Really? I didn't expect that. This is a hard problem. I mean, I didn't expect a solution like this. So I'll let you read their solution, and then we'll talk about it. Okay, so let's see, where's all that coming from, this quartic potential and things like that. Okay, so as I said, this is a very hard problem. You shouldn't blame yourself if you don't solve a thing like this. But let's see. Let the relaxed spring have length 2L. So from the mass to the ends, it is L. It is a picture like this. So the mass is somewhere here, and then we have L length of spring here, and L of that spring here. If we move the mass by distance A this way, the spring will become L plus X this way and L plus X here. And for a perpendicular extension like this, each half of the springs becomes L plus X, as we said, and the potential energy, as we know, is proportional to x squared. You will remember that for springs, the potential energy is EP equals kx squared divided by 2. Okay. We want to see how is that related to A, because that's what the choices that they gave us, A, B, C, D, E, they relate to A. So we need to see how EP, the potential energy, relates to A. So let's see. From Pythagorean theorem, we can write the following. L plus X squared is L squared plus A squared. And if we simplify and divide by L squared, we get the following. 2x over L plus x over L all squared equals to A over L squared. So that's just a simple matter of algebra and dividing by L squared. Okay, I hope everybody agrees with this. Okay, so let's see. Two extreme cases when x is much smaller than L, meaning for small extensions A. Okay, we can neglect the square term. This term here, x plus L squared, we can neglect it because squaring a really small value is making it even smaller, and it is much smaller than the term we have here, x over L. Okay, so we can neglect that second term, x over L all squared, and our equation becomes gives us basically that x is proportional to a squared, okay? And therefore, the potential energy, EP, which is proportional to x squared, is proportional now to a to the power 4. That is the quartic term that they're referencing here, okay, in their solution. In another extreme case, when x is much larger than L, so for big extensions A, when x is much greater than L, looking at that same formula, we can now neglect the linear term, because now x over L is a big number. When we square it, it becomes even bigger, and we can neglect the linear term. And in that case, we get that x is proportional to a from that equation, where we neglected the linear term, and EP is proportional to x squared, and therefore proportional to a squared. That's exactly what they're talking about. And that explains basically their solution. Okay. So let me see if there are any questions in the chat box. I did see messages from Zoom that somebody is raising their hand, but I don't see any new questions in the chat box. So if you have a question, feel free to send it through the. So somebody's asking, how does this relate to the period of this pendulum? Well, I'll let you read their solution. I just wanted to explain how approximation analysis is applied in this problem, and I'll let you look at the solution and try to understand it now that you know where the square and quartic proportionalities come from. Okay. Somebody's saying, how does this relate? The energy is proportional to the period. I wouldn't say that. I wouldn't say that. What is harmonic motion? Well, I'll let you look at some good book or join our class. But very quickly, harmonic motion is the simplest type of oscillations, like a pendulum, and maybe in this case, we were talking about, in this particular problem, we're talking about a system of a mass attached to a spring. This is mass M, and spring has constant K. In this particular problem, there was more. There was another spring, but this is the basic situation. And if you press this spring or extend it, this system of mass and spring will start oscillating. This is an example of harmonic motion. Okay. Somebody's asking, could you solve a problem like this intuitively? I could not. I had to look at their solution, and even then I was surprised. So this is one of those very hard problems that if you don't do it, it's probably okay. Okay, but make sure you do most of the other ones. All right. So this is it in terms of some advanced problem-solving techniques. We try to address something like this in every of our webinars. And this is an example of what we do, okay? Let me erase all of this, and we can move to some 2015 F equals MA problems. Annotate, clear, all dry. Okay, very good. Okay, somebody is asking, does this mean that the problems are necessarily in increasing difficulty order? No, not necessarily. Sometimes you will find easier problems after difficult problems. So the ordering, you cannot rely on that. Okay, let's see what is next. Okay, here is a problem that I will let you read, and then we are gonna solve it. Okay, go ahead, read it, digest it, think about what you would do. Okay, hopefully you had time to read this. Let me just first see, there was a question about level 1 class. Is there any prerequisite for students to know physics already? No. Level 1 class is for students who did not have any physics exposure before, but do have very solid, very good math problem-solving skills. Are there suggested labs for the class? No, again, our classes are targeted strictly at F equals MA, so we do not have any labs, and it is very problem-solving oriented. How does the airplane have friction? Would it be air resistance? Yes, exactly. There is air resistance, and as you can see in this problem, air resistance is proportional to the square of the speed of the airplane. That's a very common way to approximate it. And let's see what happens in this problem. So we have a plane with engines running at power level P0, okay, and the airplane is flying at speed V0. That's basically a type of equilibrium. If the plane was flying at a higher speed than this equilibrium speed, then the friction would be bigger and it would have to slow down, okay? It would be slowed down by this friction. If the plane was flying at lower speed, when engines are at P0, then the friction would be lower than the force of the engines, and the airplane would necessarily speed up. And basically, that's how this terminal velocity, this is a similar thing that happens to parachuters when they jump from the plane. They don't keep accelerating. Air friction really forces them to achieve this terminal velocity really quickly. And you know, if they were falling at a higher speed, the friction would slow them down. If they were flying or falling at a smaller speed, friction would be smaller. They would accelerate due to gravity until they reach that terminal velocity. Okay, and the problem is asking if the power of the engines is increased by 100%, meaning 2p0. The plane would be flying at what new speed? Okay, so here is how to attack this problem. Okay, first of all, let's recall the connection between power and force and velocity. There is a very clear formula. Force, I'll remind you, is F equals ma, and you can see the units to the right. Work is the force times the displacement, so A equals Fs, and power is the amount of work done in the unit time, so A over T. So if you write this, P equals A over T, instead of A you write F times S, you can recognize S over T as velocity, okay? So power is F times V. This is the formula that we need here, okay? And let's see what happens next. This is really a copy from the official solution. So because P equals FV, or because F is kV squared, we are trying to match the force of friction, kV squared, we get that P is equal to kV cubed. And because of that, power being proportional to the cube of speed, we have that V over V0 is really third cube of P over P0. P over P0 is 2, so third root of 2. With your scientific calculator, you can calculate that it is around 1.26, okay? And that's how you solve this problem. This is really not a hard problem, but you do need to know this little formula that P is equal to FV. And that formula is not frequently taught in school physics, but solving these problems, we learn formulas like that. They come in very handy. Okay, somebody's asking, how did you get kV cubed? Okay, once again, P is equal to FV. I think you agree with that. The force of the engine is really going to be matched by the force of friction. If it's not clear, then think about the explanation I gave about terminal velocity. Okay, if the force of friction is higher than the force of the engine, then the plane is going to slow down. If the force of friction is lower, the plane is going to speed up, and they will meet when force of friction really matches the force exerted by the engines. Okay, so really, F will be equal to F friction, and you can replace F by kV squared that was given in the problem, and you get that P is equal to kV squared times V, which is kV cubed. Okay, I hope that explains it. Okay, any other questions? So F could be replaced by force of friction at its level flight. Yes, because force of friction will match the force of the engine. If it does not, again, if FF is smaller, then the plane will accelerate. kV squared becomes bigger, therefore FF becomes bigger, and it all works until you achieve the terminal velocity. Okay. Let's see, any other questions? I guess not. So what is hard in this problem? First, I would say knowing this formula, P equals FV. Not many people actually learn that formula in school. And the second thing is thinking or knowing about the terminal velocity concept and how the forces are being matched, and how to relate all that into a nice formula like we have here at the end. Okay, moving on. So this explanation or this setup is for two problems, 14 and 15 in 2015 exam. So I will let you read the setup. 14 is a very easy problem, and 15 is harder. So let's look at the easy part first. I'll give you a minute to read it. Okay, hopefully you had enough time to read this. Basically, we have a rope, and it allows two objects on it to rotate like this. Okay, and what happens, it rotates, keeps the rope tight. The objects do not slide from the rope or this rod. They're kept there by a rope. And in the next problem, you will see there's a little complication. We will be pulling those objects towards the center, but let's wait for that. In this problem, the question is the tension of the rope. So we are given the mass of each of these objects, m here and m here. We are given omega, the angular velocity. It is what? 4 radians per second. Mass is 5 kilograms, and this rod is L equals to 3 meters. So the radius of rotation is really L over 2, 1.5 meters. Okay. What is the tension? Well, the tension is the thing that keeps these objects on a circular path, on a circular trajectory. So this tension is really acting as the centripetal force. And we know formulas for centripetal force. There is one looking like this, mv squared over r. Or if you use omega instead of v, you get m omega squared r. Okay? We know m for each object, we know omega, we know r. So it is an easy computation. It is 120 newtons. But I know that students have been confused by a problem like this, and they sometimes thought, why not 240 newtons? Because we have two objects making this rope tighter than if there was just one object, right? Well, not really, okay? It is really just between the rope and the object, okay? This object here, you can say it really doesn't know that there is another object. It's simply being pulled in by the rope towards the center by tension. And that same tension really acts on this rope, on this side of the rope towards the center. You could equally consider this problem as just one half of the rope. So you forget the other half, and you fix the rope to the center, and you can look at it like that. It's the same type of thing. So that's why it's not 240 but 120. It's not 2 times m omega squared r, but just one of them. Okay. So that was the easy part. Okay. Let's look at the hard part of this dual problem. Let me quickly erase this. Clear all drawings. Okay. So the next problem is number 15. I'll let you read it. The setup is the same. So you can start where it says 15 right here. Okay, so what is happening in this problem is, again, we have those two masses at the ends of a rod, and then there is that rope connecting them, and there is a motor that is tightening the rope and basically pulling the two masses closer to the center. So after some time they'll be here, after some time they'll be here, and we are asked to determine the work done by the motor as the two objects go from what was it, 1.5 meters from the center all the way to 0.5 meters. So 1.5 is here, 0.5 is here. So the two objects get closer, and the motor had to do some work to accomplish it. So let's see, what is the work the motor had to do? In a problem like this, you have to see if there are any external forces on the system, if there is external torque or external forces on the system. In this case, no. The motor is a part of this system, and there are no external agents acting on this system. Because of that, you can immediately say that the angular momentum will be conserved. L is the angular momentum, mvr, or m omega r squared, and you can use that. In fact, you have to use that if you want to properly solve this problem. The solution is constrained by angular momentum being conserved. So let's see. How do we relate energy and work to angular momentum? If you don't know the formula, you can actually rely on analogies with linear motion. In linear motion, we have kinetic energy as mv squared over 2, and we can rewrite that using linear momentum p as p squared over 2m. I hope that's clear to everybody. P squared, that would be mv all squared divided by 2m. That really gives you mv squared over 2. So checks out. Okay, so in linear motion, k is equal to mv squared, I'm sorry, p squared over 2m. Okay, that's how we relate kinetic energy to linear momentum. In the rotational world, we can use the analogy. Instead of p, we can write L, so L squared, divided by what do we use in rotational motion instead of the mass? What replaces the mass in formulas for rotational motion? Yes, moment of inertia. So the analogy leads us to the formula K equals to L squared over 2I. In this particular case, we have two small masses. So the moment of inertia for each of them is just mr squared, okay? And you can write the following, okay? Work is the difference between two kinetic energies, K2 minus K1. The first one will be L squared over 2I1, I'm sorry, 2I2, yeah, minus L squared divided by 2I1. If you substitute I1 and I2 with mr squared, and in fact we have two masses, so it will be 2 mr squared if you want the total moment of inertia of this system, 2 mr squared. You plug in that I2 is before the motor worked, so R is really L over 2. And for I1 you will use, no, let's see, for I2 we use the last radius, which is, I think they say 0.5 meters right here. So I2 will have that, 2 mr squared, and we will have for I1 the original radius, which is 1.5 meters. And when you plug in the numbers, you get 1,440 joules as the work. And note that L, we don't have L2 and L1 because it is conserved. It's always the same, okay? All right. So if you look at this closer, you will see that because L is conserved, we will have R changing, and therefore omega has to change. So if R is getting smaller, omega is getting bigger. So as these two objects are coming closer to the center of rotation, they will be actually moving faster. Very much like when you have an ice skater doing a pirouette, right? Okay, any questions about this? Okay, I'm looking at the chat box. I guess no questions. And I think we are very close to the end of the lecture. Let me just see if there was one or two problems that I really wanted to cover. I guess it took me longer than I expected to present some of these. But let me quickly see if there are any problems that I really wanted to address tonight. Yes, I want to address this one and then we will finish. Let me see what else I have. Yeah, very good. This is a great problem to finish with. In F equals MA, you will see, I think as a rule, a problem that looks really, really hard, okay? Something that you don't think you can solve. But then I want you to remember that problem probably can be solved using dimensional analysis, and it's probably really easy. It just looks terribly difficult, but very often it will be very easy. You just have to keep your calm, okay? So I want you to read this problem, and then we'll quickly talk about it. So quickly to summarize the problem, they're talking about a flywheel. They want to store energy as a kinetic energy of the flywheel, and the useful measure of a capacity of a flywheel is this maximum kinetic energy per kilogram that can be stored, okay? And they give you 5 formulas, and they want you to figure out which one is correct. And if you really had to do it properly, it would be a difficult task. You probably don't know enough physics to do this. However, with dimensional analysis and knowing that one of these will be correct, you can do it, okay? So if you plug in the units, and we are given that alpha is dimensionless, so you can actually forget alpha in all of these formulas. Rho is what? It is the density, so it is kilogram per cubic meter. And then sigma is a tensile strength, and they give us that it is in Pascal. So let me write. So rho, where is my pen? Okay, so rho will be expressed in kilogram per cubic meter, okay? Sigma is expressed in pascals, and Pascal is really Newton per meter squared, and Newton is from force, MA, so kilogram times meter per second squared divided by meter squared, and then you can simplify that to kilogram per meter second squared. I hope I didn't mess this up. I think this is correct. And then finally, R and H are simply distances expressed in meters. Okay, so R and H are in meters. And if you plug these units into each of these formulas, you will quickly see that only D and E are candidates that can work, okay? Only D and E give you proper units, and proper units will be energy per kilogram. That would be joule per kilogram, and of course, joule is Newton meter per kilogram, and you can work from here, okay? So only D and E are possible solutions here. They have proper units, and already it's okay to guess if you don't know which one to select among them. Okay, you could guess. You reduced 5 options to just 2. However, you can use some reasoning here. Okay, formula in D involves this ratio H over R. So that formula is saying that somehow the kinetic energy per kilogram depends on the thickness of the wheel, which really makes no sense, okay? So that is the logic you can use to reject D, and only E is what's left, okay? So again, very often in F equals MA, you will find 1 or 2 problems that look terribly hard, but can be solved very easily using dimensional analysis, okay? So with that, I will close the meeting. Let me just see if there are any other questions. Okay, yes, somebody was asking, what does L represent? In the previous problem, L was the angular momentum. That's the rotational analog of the linear momentum. P equals mv. L is equal to mvr, okay? Or more generally, I omega. All right. What is dimensional analysis? Well, dimensional analysis is exactly what we did in this problem, number 17, looking at the units and solving the problem using the units. Why doesn't it have to have H? Why does the answer not depend upon H? Well, it's a little bit of reasoning. If you had a thicker wheel in a flywheel, I intuitively wouldn't expect the density of energy per kilogram, to depend on that. Call it some engineering intuition or something like that, but you know, I feel strongly about that. All right. Somebody is asking why H over R can be absorbed into alpha, the constant. Well, H over R in terms of units will cancel meter over meter, so you're not going to see it in dimensional analysis. It doesn't you know, prevent D from being a proper solution in terms of units, but if you reason about it, like you know, H shouldn't be a factor in all of this, then I think you can solve it. All right. Would the thickness matter for rotational kinetic energy if the problem was asking for that? Well, Probably not, because let me erase this, and this will be the last question, the last answer. So the question is, if the thickness influences the kinetic energy, I would rather ask about the density of kinetic energy, okay? The mass is linear with h, okay? The thicker the wheel, the more mass we have. And also kinetic energy is only depends on, remember AK is I omega squared over 2. It really depends on I, and that will have h as a factor because of the mass. But then in the density, let's call the energy density, I don't know, W, EK over M, density of kinetic energy per mass. Those two factors cancel, and I do not expect to see h as a factor in this formula. Okay, thank you for attending. If you're interested in our classes, please visit our website and ask questions. There is a link there, there's an email, you can ask questions, and we will make sure you understand what's going on. Good luck at F equals MA, and you will find this recording somewhere on YouTube. Just search for my name and maybe keywords like F equals MA, and you'll find it. Okay? Thank you very much.